only reverse the values, finish. But when I ask you to subtract this from this, first you use the complement idea to get this, then you will add another one to the value. Then you will add these three to each other. 1 plus 1 plus 1, 1 carry over 1. 1 plus 0 plus 1, 0 carry over 1. 1 plus 1 plus 0, 0 carry over 1. 1 plus 1 plus 1, 1 carry over 1. We delete this, then we have this. It's answer. Clear? So we have two steps. First, complement. When we find the complement, then we add 1 to the whole numbers to get the value. Then we will delete the left digit always. So, example. I want to subtract this value from this. And I told you, this is important. This is very important, this part. So, 1, 0, 1, 0, 1. We want to subtract 1, 0, 0, 1, 1. We keep the top value same. 1, 0, 1, 0, 1. Here, first we use the 1 complement of this. Reverse. 1 would be 0, 0 would be 1, 0 would be 1, 1 would be 0, 1 would be 0. It's a complement of this number. 1 complement. Then we will add 1 as well. Then we add these three values to each other, these three numbers, and find the value. 1 plus 0 plus 1, 0, 1, carry over. 1 plus 0 plus 0, 1. 1 plus 1, 0, carry over. 1 plus 0 plus 1, 0, carry over. 1 plus 1 plus 0, 0, carry over. Here, we delete this, it will be the answer. Okay? Let me give you another example. So, before I give you another example, I want to talk about the 2 complement. When I talk about 1 complement, it would be only the reverse of digits. But what about 2 complement? When we talk about 2 complement, first we reverse the digit, then we add 1. So it means that when we subtract 2 digit values, we use the 2 complement of this and add that to this, and then we delete the first digit, okay? So here the 2 complement of this. The first complement would be 0, 1, 0, 1, 0. Then plus 1 give us the 2 complement. 1 plus 0, 1, 1, 0, 1, 0. Then we will add this to this directly, for example. Get that? So it means that in subtraction, we keep the top value fixed. We use the 2 complement of the second value. We add them to each other. We will delete the left digit. So here, give me the 2 complement. I want to calculate 2 complement, not 1 complement. 1 complement would be reverse of digits. 0, 0, 1, 1, 1, 0, 0. Then we will add 1 to that and give us the 2 complement. So you see, clear? 2 complement would be the 1 complement plus 1. And then in the subtraction, we use the 2 complement of the second value plus the exact value of the first one. Then we will delete the left value, the left digit of the answer. So here, the 2 complement of this, it gives us, first complement would be 0, 1, 1, 0, 0, 0, 1, then plus 1. 1 plus 1, 0, 1 carry over, 1, the same. Finish. Before I go to the digital logic, I should tell you another important thing, that is a sign binary numbers. So imagine, we know that in real world, we have minus value, we have positive value, we have minus 1, minus 2, minus 3. How we can represent that in the machine? Generally, we will assign the left digit, the leftest digit, as a sign. Okay. Then after that, other values give us the number. It's a conventional way to define a sign for the values or numbers. In ordinary arithmetic, negative number is indicated by a minus sign and the positive number by a plus sign. Imagine, we can say positive 7, minus 7. It could be 7, it could be minus 7. Okay. But what about the machine? Because of hardware limitation, computers must represent everything with binary digits. We know that we can only show everything by 0 and 1, nothing more. It's customary to represent the sign with a bit placed in the leftmost position of the number, I told you. Then we define the leftmost position of the number as a digit, 0 or 1. 0 would be positive, for example, 1 would be negative. We can assign that as well. So priori, we should know this. You know, it's important. The convention is to make the sign bit 0 for positive and 1 for negative. In this case, if we talk about signed numbers, sometimes we don't talk, so it's not important. But when we talk, you should remember the leftmost part would be the sign. 0 positive, 1 negative, okay? It's important, you should remind that. For example, the string of bits 0, 1, 0, 0, 1 can be considered as 9, generally, unsigned binary. Generally, when we don't talk about signs, everything is unsigned. But when we talk about signs, you should be careful. This one would be signed then, okay? So, or as positive 9, because the leftmost bit is 0. The string of 1, 1, 0, 0, 1 represents the binary of 25 when considered as unsigned number. But when we consider that as signed number, you should only consider these 4 digits for a number, and it would be the sign, minus 9. Clear? You should already know that, you know. When you work with a system, you should already know that your system is signed or unsigned. If it works based on the sign, then you should consider always the leftmost part as a sign, not a value. Okay? Otherwise, you do a mistake. Okay, when arithmetic operations are implemented in a computer, it is more convenient to use different system, referred to as sign complement system for representing negative numbers. In this system, a negative number is indicated by its complement. Then sometimes instead of they use negative, they use the complement of the value. Different computer, different system, different hardware, different style. Doesn't matter. I want to introduce them only to you to have information. They are not so much important. One of the parts is important here that I will tell you to learn more is the BCD format, because generally most of the computers work on the BCD format. Anyway, whereas the sign magnitude system negates a number by changing its sign, the sign complement system negates a number by taking its complement. Since positive numbers always start with 0, in the leftmost position, the complement will always start by 1. Then when you see 1, it means that's a negative. Indicating a negative number, the sign complement system can use either the 1 or the 2's complement, but the 2's complement is the most common. So, here, for example, I give you some example of this. It's a positive 9. It can be negative 9 defined by 3 base. So, sign magnitude representation. Here is positive 9, we know 9, other 0. We know that when we talk about sign, it would be the sign. So when we want to mention that as a minus 9, we keep the leftmost part as 1. Okay? It's a signed magnitude representation. But sign 1's complement, when we can use the 1's complement as minus 9, we have 9 as this. We use the first complement only to show that as a minus 9. Sometimes we can use the 2 complement of that as a minus 9. When we find this, we will add 1 to that. Okay? These are the definition of the system, different systems to define the negative numbers. Here is a table, for example. You see from 70 to positive 7 to minus 8 how we can represent positive 7, 0, 1, 1. These 3 digits represent the values, only these 3 digits. The last one would be the sign. Here until 0, 0. Then for the negative, you see we keep them, but the only difference is the leftmost bit, that would be 1. But when we use them as a sign, first complement, again for positive they are same. For negative, instead of using this style, we use the first complement of the positive one. And for the sign magnitude, for the sign complement, everything is clear, okay?
Would it tell you that sign and what complement it?
Yeah, if it comes to the exam, I specifically, also if you work in the company, also for any system you work, you should assign for it, you should know what you do. Otherwise, you will be, yeah. So, binary coded decimal, BCD, it is important. It is important, okay, because most of the system works are based on the BCD. Okay, so when we have a decimal number from 0 to 9, we can represent them directly by BCD digits, okay? That most of the computers work such as that. Because imagine, it's easier to convert the human mind to the machine. Because we have 0 to 9, then they represent each digit with 4, and it goes directly to the computer. So 0 would be 4, 0, 1, 0, 0, 1, because you know, 2, 0, 1, 0, 0, 3, 1, 1, then 4, 0, 0, 1, because it works as 1, 2, 3, 4, 8. Okay? 4, 9 would be 1 plus 8, 9, finish. So the base of BCD is 1, 2, 4, 8, but from 0 to 9, finish. Then any number, you can represent that by the BCD. For example, if you have 23, then you will use in the BCD 23, 2 would be 0, 0, 1, 0, and 3 would be 0, 0, 1, 1. Finish. You see, very easily you can write your numbers. BCD is important because it's the most convenient way for the machines to convert binary decimal to binary. For example, 22, can you convert that to the BCD? And remember, BCD is different than the binary. BCD is based on representation of each decimal digit by 4 digits based on 1, 2, 4, 8. Okay? There are some examples. I ask you, for example, to convert 481 to BCD. Please convert yourself. 481 to BCD. But it's very, very easy. And honestly, it's very easy in the exam to solve. But I see sometimes the students do mistake. They go to the binary. No, it's BCD. It's different. Convert 481 as decimal to the BCD. And give me the answer. And we know 1, 2, 4, 8 is the base of that. 1 would be 0, 0, 0, 1. 8, 1, 0, 0, 0. And 4, 0, 1, 0, 0. It would be the BCD form. Very easy. You see? The other one. Let's solve the other one. 7631. Let's solve this as well. 7631. We have this 7631 and we want to convert to BCD. So 7631. 1, 2, 4, 8. 1, 2, 4, 8. 1, 2, 4, 8. 1, 2, 4, 8. 1, 0, 0, 0, 1. 3, 0, 0, 1, 1. Because 1 plus 2 would be 3. 6, 2 plus 4. 0, 1, 1, 0, 7. 1 plus 2 plus 4, 0, 1, 1, 1. You see how much it is easy? It's the same as hexadecimal for 1, 2, 4, 8, but we have only from 0 to 9, nothing more. Yeah, and this is there are other styles, it's only for your knowledge. This is based on 1, 2, 4, 8, I told you, but other engineers, other people, they use different styles. For example, they make that based on 1, 2, 4, 2, they are more complex, but each of them for any different application have their own benefit. XS3, -1, -2, 4, 8, also maybe you can design your own system, you know. Everything should be logical, then you can design your own system. But what's the benefit is a question, because you can represent them as many different ways. Then gray codes. For gray codes is interesting. I want to show you one video because I don't want to go too much ahead, but it's interesting to know. Before everything, I want to tell you this. What's the benefit of gray code? The interesting point in the gray code is this. If you follow from 0 to 15, imagine. In the gray code, they only change each number when you go only one change of digit you have. So it's a benefit of gray code, okay? Sometimes in the system implementation, from 1 to 2, only one digit change. 2 to 3, one digit change. They design based on that to have less changes in their digits. Because, you know why? Because each digit represented by the logic gates in the real world, in the real application. So they try to decrease the complexity of their design through this way. I will provide a video for you to give you the history of that. But if the advertisement that it doesn't work. Yeah, listen to this.
In this lecture, I will introduce gray code. In the last presentation, we completed XS3 code edition, and the next type of code is gray code. What is gray code? What are its properties, and why do we call it gray code? We are going to cover in this lecture. Gray code is also known as reflected binary code, in short RBC, reflected binary code. And we call it gray code because it was given by Frank Gray. We call it gray code after Frank Gray. Frank Gray was a physicist and researcher at AT&T Bell Labs who made numerous inventions in television. Gray code is a binary numeral system where two successive values differ in only one bit. This is the most important
Yeah, I told you.
point in this presentation. I will write it down. Gray code is a binary numeral system where two successive values differ in only one bit. Two successive values differ in
Hey, you see.
only one bit.
Only one digit change.
And because of this, binary number is converted to gray code to reduce switching operation. We'll write this point down. Binary number is converted to gray code to reduce switching operation. So these are the two important points. The first one is the successive values differ in only one bit in case of gray code, and binary number is converted to gray code to reduce switching operation. Right. Today gray codes are widely used in facilitating error correction in digital communication such as cable TV systems. Now what about weight in case of gray code? Gray code is an unweighted code. There is no positional weight in case of gray code. Gray code is also called as unit distance code and minimum error code. So there are so many names for gray code. The first one is reflective binary code, RBC. The second one is unit distance code. Third one is minimum error code. And the fourth one is cyclic code. Cyclic code. Gray code is also called as cyclic code. So don't confuse yourself with these names. They all stand for gray code. Right? Now we will move to this table in which the first column is for decimal number from 0 to 16, the second column is for binary number, and the third column is for gray code. And I will use this table to explain you this point. Two successive values differ in only one bit in case of gray code. So the first thing that we have to do is to convert the decimal number to binary, and then we will convert these binary numbers to gray code. In this lecture, I am not going to explain you how to convert binary to gray code. I will explain this in the next lecture. I have already completed the column for gray code, and now we will see why switching operation is reduced in case of gray code. Let's try to analyze 3 and 4. 3 in case of binary is 0, 0, 1, 1, and 4 in case of binary is 0, 1, 0, 0. I will consider a case in which we are having 3 and we want to switch to 4. So let's see how many bits we need to change. B3, B2, B1.
But in the gray code only one
In case of gray code,
only one switch.
we have B3, G3, G1, and G0. Now let's see how many bits are changing in case of binary number system. 1 is changing to 0, B0, 1 in case of 3, and in case of 4 it is equal to 0. So B0 is changing, B1 is also changing from 1 to 0, B2 is also changing from 0 to 1, and B3 is same, 0 and 0. Now we will analyze the same case for gray code. G0 is same, G1 is same, G2 is changing from 0 to 1, G3 is same. So you can clearly see, to switch from 3 to 4, we need to change 3 bits in case of binary, whereas in case of gray code, we only need to change 1 bit. That's why gray code is called as unit distance code, and switching operation is reduced in case of gray code. Let's take another example. Let's take example of 7 and 8.
Is 16 and
Binary,
the same?
you can see.
No, it's only put as one for zero.
B1 is changing.
So you see we have another.
And B2 is also changing. So to switch from 7 to
No, I put this in only for information. The table also I showed you. The main important thing I tell you what. The DCD is important, the subtraction is important. And it's good for your knowledge to know how gray
You can
code
also
goes.
check for
Right.
any other case and you will
And
find
other
that
codes also
one
are the same. You know, they define in different way for their own
that
system.
the statement is
have
now
less
verified.
numbers.
So this is all for this presentation. Now we will move to more problems.
Then we come back to our class. Yeah. So it's a benefit of the gray code. So now I want to review the digital logic and gates and then finish the presentation. So I know all of you know the digital logic. Yes, in 21 you know. So binary logic deals with variables that assume discrete values and with operators that assume logical meaning. It's very important. We know in the digital logic we have only two values, 0 or 1, nothing more. Then we also need to have ways to combine different logic signal or condition to provide logical result. When we deal with logical circuit, in the computers, always we have logic circuit, digital circuit. We not only need to deal with logical function, but also need some special symbols to denote this function logical diagram. There are three fundamental logic operations. They are very, very important, from which all other functions, no matter how complex, can be derived. Okay? So these functions are named as AND, or, NOT. Only we have these three. Everything is based on them. Yes, there are many advanced things, complex things, but the base is only these three functions, AND or NOT. And each of them has different specific symbol and clearly defined behavior. And the AND operation is represented by dot, okay? Or by the absence of operator. For example, x dot y equals 0, or x y equals 0. It's AND. Are all read as AND. The logic operation of AND is interpreted to mean if x and y are 1, z will be 1, otherwise z will be 0. Okay? So the OR. The operation is represented by plus. Sign of example, x plus y equals z. It means in the mathematics, the normal math is x plus y, but here we say x or y. Okay? OR is represented by plus. And in the case that if x or y or one of them would be 1, the answer would be 1, otherwise it would be 0. We know. Then NOT. The operation is represented by a bar or prime. There are two ways to represent the NOT. For example, if I have x prime or x bar, both of them means NOT of x. Okay? So then NOT x equals z, meaning if z is x is 1, z is 0, if x is 0, z is 1. Okay? So 3, AND or NOT. You know already. Then basic gates. The basic building blocks of computer are called logical gates or just gates. Gates are basic circuits that have at least one and usually more input. Imagine you have at least one or more input and exactly one output. Always for a gate we have only one output, not more. Input and output values are the logical values, true or false. We say them true or false. True is 1, false is 0. In computer architecture, it is common to use 0 for false and 1 for true. Gates have not memory. This is the main difference in the combinational circuit and sequential circuit that you will learn in next sessions. That sequential circuits have memory, combinational circuit have not memory. Gates also have not memory. Philip Delap has memory. You know. The value of the output depends only on the current value of the input. Why? Because they have not memory. A useful way of describing the relationship between the inputs of gates and their output is a trough table. It's important. In the trough table, the value of each output is tabulated for every possible combination of the input values. Okay? So, depends on the number of inputs. We have the input in the trough table and then output. Remember, always we have one output. Then it means that maybe we have 2 inputs, 3 inputs, 4 inputs. Our trough table numbers would be changed, but always one output. So, AND gate. It's a representation of the AND gate. You should know. It's very important. It is AND. Here, how many inputs we have? 2. Always we have one output. And then we can represent input as I1, I2, X, Y, A, B. Any A1, A2, any definition for the symbol is okay for. So the important thing is this trough table. So it's a trough table. How many inputs we have? 2. How many outputs we have? 1. So because we have 2 inputs, how many conditions we can have? 2 power number of inputs is important. 2 power n. N is the number of inputs. So what it means that here we have 2 inputs, 4 conditions. It would be 0, 0, 0, 1, 1, 0, 1, 1. We cover all of the conditions. And because it's AND, only in this condition the output is 1. Otherwise, 0. Clear? We can represent it as I1 times I2. I1 point I2 or I1 I2. Then OR gate. OR is represented as this. Okay, it's an OR gate. See the difference between AND gate and OR gate as a symbol. Then here again we have two inputs. What it means? It means that we have 4 conditions, 2 power n, the number of input. Again 0, 0, 0, 1, 1, 0, 1, 1. But we know that because it's an OR, in this case we have 3, 1. Only in the case that both of the inputs are 0, the output would be 0. Clear? And we represent that as I1 plus I2, I1 or I2. Then the NOT, it's a symbol of NOT, very clear. In the NOT we have always 1 input, 1 output, we cannot. Yes, we can have, no, we cannot, only 1. Then we have, if the input would be 0, output 1, if input 1, output 0. And bar or prime, it can be represented as I bar or I prime. Both of them have the same. Then we have NAND gate. The NAND gate it would be not AND. Okay, NAND, not AND. We have AND, then we put the not at in front. Then here would be not AND. It means that if we have 4 conditions, because we have 2 inputs, 0, 0, 0, 1, 1, 0, 1, 1, because it's a not AND, it means 1, 1, 1, 0. Inverse of the output of AND. And how we can represent that? Well, by this. There are other symbols also to represent that. Here, such as this. It would be I1 not, I2 not, then OR. It would be the same, the answer. Here, and not. It's the same because and it's a representation I1 times I2 or I1 and I2, then not, or prime. Here, we can extend that, then it would be I1 not plus I2 not. Why? Because the inverse of and would be OR. Okay? It's important. Then we have NOR gate or not. Here, NOR or not. Here would be 1, other 0, because it's not of OR. Again, there are other ways to represent that, as you see, or not, and not, and. You know why how it comes? How we can find this? It would be I1 plus I2 not. Then if we extend I1 not plus, times or and I2 not. It comes from that, you see? Yeah. Clear? Then we have XOR. It's an XOR gate. It's another basic. You know already. It's XOR or XOR. Then we have I1 and I2. Here it's a bit different style. In this case, if one of the input is 1, the other one is 0, the answer is 1, otherwise 0. Or if we have more inputs, if the odd number of the inputs are 1, the answer would be 1. If the even number of inputs are 1, the answer would be 0. Okay? So imagine here, when both of them are 1, 0, or both of them are 1, 0. When one of them is 1, one of them is 0, 1. So imagine if we have 3 inputs, in the case that we have even odd number of 1 in each row, the answer would be 1, otherwise would be 0. It's a XOR, okay? And it's a representation of XOR. Imagine inside the circle there would be a sign, positive. And then its representation would be this, I1 not, I2 plus I1, I2 not. These are important, it's just to remind you because I know you already know that. And the last case, XNOR, is not of XOR. So, in this case, if the even numbers of 1 are in the row, the answer is 1, otherwise it would be 0. It's a not of OR. Here, as you see, here, 1 and 1. Here, not of OR. Okay? And then, it's a representation, then I1 not, I2 plus I1, I2 not, the whole is not. Then Boolean algebra, then we have another topic that is important to review. Boolean algebra, one of the primary requirements when dealing with details is find a way to make them as simple as possible. It's important because we can simplify our equation, our circuit by this. This constant requires that complex logical expression be reduced to simpler expression that nevertheless produce the same result under all possible conditions. One tool to reduce logical expression is the mathematics of logical expression, which is called as Boolean logic. Boolean algebra or Boolean algebra. Boolean algebra is a form of arithmetic that deals solely in ones and zeros. It has only three operators, again, or, not, and, nothing more. And with them, we can extend the expression, we can reduce the complexity, something. There are some laws for that is important. A plus B equals B plus A. A times B equals B times A. Or in other words, A or B equals B or A and B equals B and A. Okay, we know that. Then we have an associate law, A plus B plus C, A plus B inside the bracket, plus C equals A plus B plus C inside bracket. Or AB times C would be A times BC. It's clear. But remember, plus and would be or and not and. Or and. Here, A and B or C, it would be AB plus AC. Clear. Here, A plus BC would be A plus B times A plus C. We can use them to simplify our expression. And then we have the identity law, A plus A times A. A plus AB plus AB naught would be A. Do you know why? It's interesting to know this. I will solve for you. AB plus AB naught would be A inside the bracket, B plus B naught. It would be 1, A times 1, clear? And here, AB times A plus B naught. It gives us A, the same. You can extend that yourself. Do you want to extend that? Let me extend. A plus B, because you have question from this form as well. In the tutorial you will see and you will solve, I will solve. It's important, I like this kind of question. Then it would be because it's math. A times A plus, I multiply first this to this, then A times B naught. Then B, AB, then B naught. B times B naught would be 0. Then A, B naught, then we have these three values. Then it would be A plus A, B plus B naught. It would be 1. Then it would be A plus A, it would be A. You see? You can extend and find it. Another rule is this. A plus A times B would be A. Do you know how? I can solve this also. A plus AB. A plus AB. It will be A times 1 plus B. Okay? 1 plus B would be 1. A. Clear? And then A times A plus B would be A. We can extend. A times A plus A times B. A plus AB. It will be this, then would be A. Clear? Then 0 plus A. 0 times A, 0. A plus 1, 1. A times 1, A. A plus A naught, 1. A times A naught, 0. A plus A naught B, A plus B. A times A naught plus B, AB. These are the rules. And the last one, the Morgan laws, is very, very important. A plus B naught would be A naught, B naught. It's very important. A naught, A, B naught. A naught plus B naught. Clear? You will have one question from this generally. So I give you expression, complex expression. I ask you to complement that, to not that. Then you should know these rules well. Then you can. Clear? You know already these, but I repeat. Do you want to solve before I finish? Do you want to solve this as well for you, or not? You want? So let me, because I like math. You know, some math. Here we have A plus A naught B. It would be A plus A naught times A plus B. It would be 1. Then it would be A plus B. Finish. You see how much they are easy? The other one. A times A naught 0 plus AB. Finish. A times A naught 0. A times B, AB. You see they are very easy if you get the rule. Nothing more. Then imagine in the example of A plus B naught, I give you xy plus y, z, then I ask you to make not that. Then you should separate them not, and then you can continue and solve. Let me give you one example before I finish. A more complex example I give you, for example, it can be a question. AB plus BC not. We want to solve that. It would be AB not and BC not. Okay? Then we extend. AB naught would be A naught plus B naught, then times inside the bracket, B naught plus C naught. It will be answer. You see how much it is easy? You will have some kind of this question. We have practice. If you practice everything, you know the base, then it's okay? Happy? Hopefully now we can finish the class now. If you have any question, ask me. Otherwise, see you next week. Next week, you have a lecture.